Welcome to Lecture 1, which is in fact, I'm just not renumbering them, but this used to be Lecture 1. What I would like to do is make a change right here, okay? Syllabus, no longer part of Lecture 1. We did that at the beginning of Lecture 5. We're going to start the second half of the course, which means that we are going over scientific notation, significant figures, metric system. Okay. In this video, you need a calculator. You need a calculator that is not a graphing calculator for quizzes. You can use a graphing calculator while you're doing the videos and on your homework and in recitation, but really it would be best if you use the same calculator for everything. And it's really going to come into play doing the things that we're going to start doing for the rest of the semester. So I will not allow you to use a graphing calculator in the quiz, and when we're taking quizzes and tests, and that is spelled out in the syllabus, and that's a pretty much, overall South policy. All right, so you've already watched some of the previous videos in the first half of the course. I am using a different software to record. It's going to be a little bit different in terms of what you see. I cannot write on the notes. I believe with this recording you can see me move the cursor with this program, but I will be going to another program to do writing. So when we get to practice sections, I will switch to Notebook as the name of the program, and that's what I will use to work problems. So the first thing we're going to talk about is scientific notation, and we use a lot of scientific notation in chemistry because we are talking about really small things, atoms and molecules, and we are going to, because they're small, we have a lot of them in any given sample, millions and millions and millions of molecules or atoms. All right, so we're going to first review what scientific notation means, whether you have a positive exponent or a negative exponent, what that means. We are not going to do a whole lot of moving the decimal around. I want you to be able to do scientific notation on your calculator, but I'm just going to remind you here at the beginning about those exponents. So for numbers right here, for numbers less than 1, you, which means you have a 0 in front, you are always going to take that decimal and you're going to move it behind the first integer, which in this case is the 3. So however many times you had to move it is the exponent. So it would be 1, 2, 3, 4. So this number in scientific notation is 3.45 times 10 to the negative 4. Okay. How would you then, going backwards, you would take that decimal where it is, right here in the second question example, and you would move it, because it's a negative exponent, you know you're going to move it to the left. So I'm going to move it to the left 5 spaces because it takes 1 exponent to move it to, to the left of the first integer, and then you'll put 5 zeros in front. Okay. When we get to the Notebook program, I will show you those answers written out. Okay. Then for numbers greater than 1, you take the decimal. It's implied that it's at the end of a number, of course, and you move it behind the first integer again. So however many times you moved it, 1, 2, 3, 4, 5, 6. So the answer here would be 2.34 times 10 to the 6th. And then going backwards, you're taking that decimal from behind the first integer, and because this is a positive exponent, you know you're moving it to the right. So 1, 2 moves it 2 spaces, and then 2 zeros to round that number out. Now what I'm going to do is pause the video so that when I get to the Notebook program, I have these numbers, these answers at my fingertips, and we'll also be ready to do the practice. All right, so as promised, the answers to the examples that were embedded into the notes, the first two moving from where I had numbers smaller than 1, My first answer was 3.45 times 10 to the minus 4. My second answer was 0.1234518. My third answer for positive exponents was 2.34 times 10 to the 6th. And the fourth example was 64,300 written in regular decimal notation. And that's the first thing we're going to do here in the practice. We are going to take those exponents, and because this one's positive, I know I'm moving that decimal to the right. If this one's negative, I'm moving that decimal to the left. Now, what the best thing to do here, especially since we're getting into the math portion, is to stop the video, try these examples, and then start it back up, pause it, start it back up, and you can check your answers. Okay? All right, so number 1, I am going to move that to 3 spots to the right, so it's going to be 5. Now, I moved it 1 by bringing it from here to here to 3. So the answer to 1 is 5,200. Number 2, it's a negative exponent, so I will have 1 less than this exponent in zeros because it takes 1 to move it in front. So 0.123965. Negative, so 1 0 in front of the 8 5. Positive, moving it behind the 7 and the 1 takes up 2 of those exponents, and then I need 2 zeros to give me the 4, so 27,100. 36 would be the answer to 5. Positive exponent, so twice, 645.2. 1 time, which only brings it to the left of the first integer. And then this last one, 2 zeros in front of the 64. And there are our answers in decimal notation. Now we're going to do the opposite, putting these examples into scientific notation. All right, again, I'm not going to concentrate so much on what we're doing here. I'm just reminding you what scientific notation means. Next thing we're going to do is learn how to do it on our calculators. All right, so this is a number greater than 1. Decimal is here. I need to move it behind the first integer. So that means I need to move it 1, 2, 3, 4, 7.8 times 10 to the 4th. Now, how many places do I write it at 7.8 times 10 to the 4th? 7.80 times 10 to the 4th. That involves significant figures, and we will be talking about that, I believe, at the end of this lecture. And it's a very important topic in chemistry when you're starting to talk about numbers. Number 2, this number is less than 1, so I'm going to still move that decimal behind the first integer, which means I need to move it 1, 2, 3, 4. So 5.3 times 10 to the negative 4. Another way to look at this is I've got 3 zeros in front, so it's the reverse of what we did in A. So my exponent, since I have 3 zeros, will be times 10 to the minus 4. I have 2 zeros here on number 6, so my exponent is going to be times 10 to the minus 3, and so on. All right. Number 3, it's a number greater than 1, 2.5 times 10 to the 2nd. The next one, I don't have a lot of zeros, so I could leave it like this. 2.687 times 10 to the 3rd, moving it from here to here. If I needed to decrease my accuracy, I can do that easily in scientific notation, but I would be rounding, and whether or not I went up or down here would depend on the value of the number here. All right? And then for number 5, 1.6 times 10 to the 1st. Number 6, 4.3 times 10 to the negative 3, so 1 more than the number of zeros. 8.75 times 10 to the minus 1. And then this last one, 1.2654 times 10 to the minus 2. I had 1 zero here, so this is 1 more than the number of zeros. Again, If I need to drop my accuracy here, my number of significant figures, as we'll talk about later, 1.27 times 10 to the minus 2 would be the same number, but with less accuracy. This has 1, 2, 3, 4, 5 significant figures. This has 3. I could drop that further to 1.3 times 10 to the minus 2. I can do this in scientific notation and not lose the magnitude of the number. Very hard to do in a number like 250. If I want to leave that in regular decimal notation but decrease the number of significant figures, I'm kind of stuck because it needs to be 250, and I'm showing that here. But if I just drop that 0 off, it'd be 25 and not 250. So anyway, we're going to get to significant figures in just a moment. But they really come into play when you're putting numbers into scientific notation. All right, I'm going to pause and nope. Yes, and we're going to talk about calculator. So get your calculator. All right, what I'd like to do next is show you how to use your calculator in order to do scientific notation. So I've got some calculator images here. You can look at a few of these scientific calculators and show you the buttons you need to be looking for. So Casios are very popular, and so what you're going to do when you put a number in scientific notation, you're going to be looking for this button right here, this EXP button, which is down on the last row, kind of in the middle. You are not going to press the multiplication key. You are not going to put in 10, and you're not going to find the caret key wherever that is. You are going to, so if our number were 3.1 times 10 to the second, you would press 3.1 EXP 2. All right, that's this calculator. Different calculators, and this is why you need to have your own that you use on tests all the time, because they're all different. So if you run and borrow somebody else's, they all are a little bit different. All right, here is a RSB. The exponential key is down here at the bottom, last row, kind of on the right. So again, 3.1 EXP2. It's the same thing as saying or writing 3.1 times 10 to the second. All right. Graphing calculators, which you should not be using on tests, are different even still, and some of the scientific calculators operate the same way. This is not a very good image, but the key you are looking for is a second function, and it's labeled EE. That's the same as the EXP on the scientific calculators. So if I were doing my 3.1 times 10 to the second, it would be 3.1 second EE, which is right here, kind of in the left in the middle, and then 2. All right, that's how I put that number into the calculator. And then from there on, it's the same as if you were doing any other calculation. If you're adding, you press the add key, and so on. Let's see, I had another one picked out. Here's a slightly different one. Okay. That EXP button is right here on the left-hand side in the middle. So you would go 3.1 EXP2 using our same example. So all of them are a little bit different. Okay. All right, so you need to learn how to use your calculator and have the same one all the time. All right, we're going to do some practice using our calculators. So here's the practice that's in the notes on doing scientific notation. Now, one thing that did not come out very well when I ported this over were these exponents. So they're a little bit small. That's 10 to the 23rd. Here it's 10 to the 4th. They're going to be easier to see in the notes. Okay, if you have those in front of you, which I strongly suggest you do that. So what I'm going to do is, actually, I'm going to pause the video and get all the answers, because I don't have them written down in front of me. And you do the same thing and come back, and we will make sure that you're punching those numbers in right and getting the correct answer. All right, if you, what I'm going to do is kind of walk you through those first two with the answers, and then I'm going to pause again and just generate all of the answers so you can check yourself. All right, so based on what I told you earlier about the putting it in your calculator and showing you the keys, you would have put this in as 6.02 and either EE or EXP23. No times, no 10. 6.02 EE or EXP23, and this implies multiplication here, times 8.65 times 10 to the 4th. 8.65 EE or EXP4. And this is the answer you should have gotten. Now, when I put that in my calculator, I'm going to do it again really quickly, I probably have a lot more digits after the 2, 1. And what I have done is I have rounded. And why have I rounded the way I have? It's because of significant figures. So my calculator tells me 5.2073 times 10 to the 28. My original numbers were only to 2 decimal places. So or 3 significant figures. So my answer needs to reflect that. My answer cannot be more accurate than the numbers that I put in. So I'm kind of introducing significant figures as we go on. When you put in the negative exponent on the second one, you are not going to use the minus key. You're going to find a plus minus key. Okay, so 6.02, I'm going to go through this, and 6.02 EE23 times 9.63 exponential negative 2. And this is the answer you should have gotten. Again, I rounded based on the numbers that I started with. Okay, so I only have 3 significant figures here. Let me go back to the images and show you what I'm talking about with that negative. All right. It's been my experience that students don't really understand how to do their calculators, especially when it comes to scientific notation. So if I just click on this Casio, again, very popular pick for a calculator, the key you want is this plus minus key over here on the left edge in the middle, not the negative key. That's a function key. This changes from positive to negative on the left in the middle. So you need to find that key on your calculator. All right, back to our practice. I'm going to pause and get all the rest of the answers, and then we'll come back and check. All right, we're back. Every time I do that, I go back to that screen. Okay, here are the answers up through number 12, and let's talk about a few of them. Should have been no difficulties with number 3 or 4. Now, these negatives, negative numbers, and especially when you're combining it with a negative exponent, I don't actually put this negative into my calculator. The order of operations on how to do that, it can be very tricky depending on the calculator. So I just know I have a negative times a positive, my answer is negative. I have to put these in there, but I don't really have to put this in there. Okay, so that's what I did. For number 5, shouldn't have been a problem. Number 6, just straight division. Now, number 7, did not put the negatives that are in front in there, but I knew that a negative times a negative gave me a positive. When you get to 8 through 12, be careful of your order of operations. This number times this number, and then either press the equal sign to divide by the denominator, or put this in parentheses in your calculator and then divide by the denominator. Your calculator will know if you do this wrong. If you press this times this and then say divide by that, what you're really doing is you're saying 5.4 times 10 to the 4th times 2.2 times 10 to the 7th divided by 4.5 times 10 to the 5th. And that's a different number than this one. So either put the 2 terms in parentheses and then divide by the denominator, or vice versa if you have the 1 number on top, 2 numbers on the bottom. Or I just press the equal sign every time I do an operation. Okay? Here I had this times a negative divided by a positive, so I knew that my answer was going to be negative. Here, this times a negative divided by a negative, so I knew that my answer was positive. This times this divided by a negative, answer is negative. And this times a negative divided by a positive, my answer is negative. So those are the answers through number 12. All right, and now I'm going to pause and finish up the answers for the rest. All right, we're back. We had 2 questions left to go. To my screen. When I brought this in from the notes, this 8.9 times 10 to the minus 3 on the denominator was left off, so I went back. I knew that that looked weird, and put that in. So the answer when I do all 3 numbers is 4.3 times 10 to the 16th. Negative times a negative gives me a positive. Notice that 1 decimal place are 2 significant figures, so that's what my answer needs to be in. Same thing here. 1 decimal place, 1 decimal place, 1 decimal place. So I rounded this number. This number in my calculator was 1.4336 times 10 to the 45th. Do not write all the numbers that your calculator has. Look at the numbers you start with, and that dictates how you're going to round your number. Negative times a negative, so it all ended up being positive. And that is the practice on your calculator with scientific notation, and we will be doing scientific notation on the calculator throughout the semester. All right, our next topic is significant figures. The rules for the significant figures can be found on pages 15 and 16 of your textbook, and I've reproduced those here. Basically, there are a lot of picky zero rules. And I will try to, abbreviate all the rules as best I can. But it's right here is where I've done that abbreviation. It says basically for numbers greater than 1 and with a decimal, every digit is significant. Okay? So, examples right here. Every number, 6 significant figures. 1, 2, 3, 4, 5, 6. That is a number greater than 1 with a decimal. Here's another number, greater than 1 with a decimal. 6 significant figures. Here's another number, greater than 1 with a decimal. 6 significant figures. Okay? Where it becomes tricky is when you have a number less than 1. Here's another number, greater than 1 with a decimal, 3 significant figures. So that is the big one. If it has a decimal and the number is greater than 1, count everything. Without a decimal, zeros in the middle are significant but not at the end. So an example of that, let's see, numbers without a decimal. Here, that's out of decimal. Here, zeros at the end are not significant. There is no decimal. So this only has 3 significant figures. Let's see if I can find one with them in the middle. I don't see one, but we're going to do an example. So let me scroll down and see if I can find, we're going to do some examples. Let me see if I can find one that goes along with that rule. That's got a decimal. That's the zeros are at the end. When I go to the practice, I will come up with one because I don't see an example like that. Okay. So, without a decimal, you gotta be careful. Zeros at the end are placeholders. Now, numbers that are less than 1 also have some picky rules. Placeholder zeros for numbers less than 1 are not significant. Okay, but everything else is. And generally, numbers less than 1 have a decimal. So, here, these are placeholder zeros on this number. But this one at the end is significant. It's only the ones that come in front when numbers are less than 1 that you don't count. So this number here has 3 significant figures. Okay? There's another number here. These zeros right here are not significant. That's why this number only has 2 significant figures. All right? So now we're going to do some examples, and I will start off with an example of the one we did not have an example of. So going back to Notebook, and I already have these copied. I guess I don't. All right, so here we are with our examples of significant figures. The one that I was referring to that I could not find is when you have a number that is has no decimal but has zeros in the middle. So this number would have 4 significant figures. And I also often abbreviate sig figs as SF or sig figs. Okay, this number here, as we'll see in the examples, has 3 significant figures. See, that 0 in the middle is significant, but these ones at the end are not. Put that there and everything's significant. 6. All right, so let's go through these examples. Let's do the first couple together and then pause the video and try the rest and come back for the answers. All right, so we've got one, this has got a decimal, it's greater than 0, greater than 1, so everything is significant. 6. No decimal, zeros at the end are not. 2. Decimal, everything significant, greater than 1, 1, 2, 3, 4, 5, 6, 7. Okay, pause the video and come back for the answers. 5 on number 4, 2 on number 5, 3, 1, 2, 3, 4, 1, 2, 3, 4, 5, 6, 3, 1, 2, 3, 4, 5, 6, 6, 7, 8, 1, 2, 3, 4, 5, 3, 6. Your book is going to tell you that for this number here, a whole number that has no trailing zeros has an infinite number of significant figures. I think that's kind of crazy, but we're just going to go with 1, 3, and no decimal here, but there are no zeros trailing, so all of your non-zero integers are significant. So 1, 2, 3, 4, 5, 6. All right, now we're going to do some of that rounding that I kind of introduced you to as we were doing the scientific notation. So here I've got it, the number 120,000. But is it 120,001 and so on? So I don't know. That's why these are called placeholders. If I just round it to 3 and say 120, I've lost the magnitude of this number. So this is where scientific notation comes in. 3 significant figures. 1, 2, 3, 4, 5. This number is 1.20 times 10 to the 5th. That is 3 significant figures, and I have not lost the magnitude of my number by putting it in scientific notation. So that's the answer to number 19, and that's really the only one you need to do that with. I would be tempted to do it with number 21 because that's just kind of a crazy number to write to 3 significant figures with all those zeros. But anyway, 3 significant figures, number 20, so 5.46 because the last number that you're dropping off is greater than 5. Here you could leave it as 0.000 since those don't count and say 877, what you're dropping off is greater than 5, or put it in scientific notation. 8.77 times 10 to the minus 4. Same thing, I haven't written all that stuff. Here, we're going to round as if this were a number on our calculator. The integer where we're dropping is greater than 5, so 4.54. Right? You have to pay attention to your numbers given in a problem, as I alluded to in the scientific notation practice. Whatever number is smallest is what you're going to use. Now, your book makes a distinction between addition and subtraction and multiplication and division. I really don't think there is a distinction. 1.2 times 4.567, my answer can only be to 2 significant figures. So if I put that number in on my calculator, find my calculator, my calculator says that it's 5.4804, but I'm not going to write that. I am going to write 5.5 because I can only report this to 2 significant figures. Okay? Same thing with division, same thing with addition and subtraction. This number with the smallest number of significant figures limits what your answer can be in. All right, back to the notes. And the next thing we're going to talk about is the metric system. And students just love the metric system. Now, what we've done up till now is done a bunch of numbers without a unit. Nothing behind it. No grams, no milliliters. That ends now, because everything we do from now on out is going to be a number and a unit. And this is very confusing to students because you've got both things to deal with. But the units are your friend, because they are going to, if you focus on the units and do what must be done to get the units straight, it's going to tell you how to do the problem. This is a new kind of a new approach. Those of you who had chemistry in high school might have had the picket fence, you know, however, whatever your teacher called it. But that's what we're going to be doing. We're going to be doing dimensional analysis. Now, in order to do dimensional analysis, we need to have conversion factors. So page 24 of your textbook has two sets. There's one that is metric only, and that's in the top half of the page, I believe. And on the lower left are English to metric conversions, and they're not the same. If I am going metric to metric like I am here, I'm going to use that table of prefixes. What I have here bookmarked is a table of prefixes, so let's go there, and this is for the metric system. You are expected to know some of these, and the ones that you need to know are the ones that are bolded here in this table. You need to know giga, or giga, mega, kilo, deci, centi, milli, and micro. You must know those. Now, when we go metric to metric, the thing that you're going to want to focus on is this whole power thing. Okay, this column right here, power. I'll be referring to that, okay, as we go through. Now, this table here does not do the base. The base measurement would be between here and here. And the base is grams and liters and seconds and calories and joules and any number that does not have a prefix. All right, so prefixes below the base, all of these, are less than the base. How much less? Powers of 10. Deci is 1/10 of the base. Centi is 100th of the base. Milli is 1,000th, or 10 to the minus 3 from the base. So I am going to be referring to these powers, and you can also use this last column here, to do your conversion factors, as you will see in the notes. Okay, so let's go back to the notes. So first thing we're going to do is we're going to introduce this idea of conversions and dimensional analysis. Is we're going to do a metric to metric, which means you're going to use the table either that I just showed you online or the one in your book, not the one on the lower left on page 24, the one in the middle or the top. We want to go from milli to meter. So I want to go from a prefix unit to a base. Meters has no prefix in front of it. So milli has 10 to the minus 3 in front of it. Meter has, you can think of it as having a 1. So how far apart are they in terms of powers of 10? They are 3 powers of 10 apart, or 1,000. There are 1,000 of the smaller ones and the larger one. Milli comes below meter in the table. It means and they are separated by 3 powers of 10, so there are 1,000 of the smaller and 1 of the larger. Now, how do I know which to put on top and which to put on the bottom? I want to go from milli 2 meters. So the one I'm going to needs to be on the top. The one I'm coming from needs to be on the bottom. So when I multiply these two things, they cancel. Okay? That's one way of looking at it. If you want to use the book's table and the one online more literally, then take that column on the right, which says 0.001 meters for milli, and that stays with the meter. Okay, whatever number, let me show you what I'm talking about, whatever number is here on the right in this table, okay, stays with the base unit. All right, so how do I do that? Okay, so I'm trying to get out of millimeter, so millimeter needs to be on the bottom. Trying to get to meters, so that part goes on top. If I'm using the table literally, then I will put the number that goes with the base unit on top. I kind of like the positive, the powers of 10 approach better, but this gives you exactly the same answer. All right. If I want to go the other way, I'm going to use the same conversion factor, but I'm going to flip it because now I'm going from meters, so meters needs to be on the bottom, and what I'm trying to go to needs to be on top. Okay? So we're going to do this practice, all right, so that we can practice our metric to metric conversions. In lecture 2, we will work on other conversions and use the concept of density as a conversion as well. Okay, so I don't think I've got this on the thing here. All right, so I'm going to walk you through a few, and then again, I'm going to we'll pause the video and get the answers there and then go over them. All right, so we're going to go out of milligrams and into grams. Milli is 10 to the minus 3. Grams is a base unit, so it's like a 1. They are 3 powers of 10 apart. So there are 1,000 of the smaller and 1 of the larger. So I will go 2,000 milligrams times, I want this on top, 1 gram has 1,000 milligrams. Okay, so 2 is the answer. Right. Now I know that you've probably learned King Henry's Daughter Dates Cookie Monster in high school. I really think we need to move beyond that because we need to focus on this method of problem solving where I'm using the units in order to be successful in chemistry. Cannot emphasize it enough. Next one, I'm going liters is a base unit, so it's a 1. Milli again is 10 to the minus 3. So again, I've got 1,000 of the smaller in the larger. So 5 liters times, when I get rid of liters on the bottom, 1,000 milliliters on top. So my answer to number 2 is 5,000. Okay? Now, number 3 represents a metric to metric, so this is the way to do it. This says 10 to the minus 2. This says 10 to the minus 3. They are 1 power of 10 apart, which is smaller than this one. So there's 10, 1 power of 10, 10 millimeters in a centimeter. I want to get out of centimeters, so that part needs to be on the bottom. And we have 10 millimeters in a centimeter. Okay, this is what we're trying to do, and it's telling us what to do with the numbers. So my answer here is 160. So again, centi means 10 to the minus 2. Milli means 10 to the minus 3. They are 1 power of 10 apart. 10 smaller in the larger. Right? I'm just going to walk through these next ones. I'm going to do the conversions like pretty fast. Okay, so 104 kilometers. Kilometer on the bottom. Kilo is 10 to the third. This is a 1. There are 1,000 of the bigger, smaller, and the bigger. So this answer here is 104,000 meters. Okay, number 5. Base unit, grams. I want to get rid of the grams. And in fact, this is 10 to the third. This is 1. Grams are smaller. So the 1,000, the 3 powers of 10, goes with the smaller. and the kilogram goes on top because that's what I'm trying to get to and get out of grams. So this is going to be 0.198. All right. Number 6, meters to kilometers, so 2,500 meters. I want to get out of kilometers. This is a 1. This is a 10 to the third. Meters is smaller, so there are 1,000 meters in a kilometer. So 2,500 divided by 1,000, 2.5 kilometers. 10 to the minus 2. This is a 1. There's 100 centimeters in a meter. Because they are 2 powers of 10 apart. I want to get rid of centimeters. This 100 stays with the centimeter, the smaller one. So the answer to this is 4.8. All right, 75 milliliters. Want to get rid of that. Milli is 10 to the minus 3. This is a base. So they're 1,000 apart. Milli is smaller, so the 1,000 stays with the milli. Put it on the bottom to cancel. Okay, and it's dividing by 1,000 here. So let's see, 0.075. Okay, do a little erasing there. Okay, now I need to do a lot of erasing so that I have some room, or I can extend my page a little bit. There we go. All right, number 9. We are going from grams to milligrams. This is a base unit. This is 10 to the minus 3. Milligrams is smaller, and I want it on top. So 65 grams. Focus on the one you're trying to get rid of. That goes on the bottom. 1,000 milligrams per gram. So the answer here is 65,000. Right. Number 10, kilograms to grams, 5.6 kilograms. Kilograms on the bottom. Grams is smaller. They are 1,000 apart from each other. So the answer here is 5,600. 50 centimeters. Want centimeters to go away, so it needs to be on the bottom. Meter needs to be on the top. 10 to the minus 2. This is a base. So 100 of the smaller in the larger. So the answer here, erasing, is 0.5. Okay. Metric to metric, 10 to the minus 2, 10 to the minus 3. Milli is smaller. There are 10 of those millimeters in a centimeter, and I want that part on top. The 10 stays with the smaller, 1 centimeter, so 63 is my answer here for number 12. Okay. 10 to the minus 3, 10 to the minus 2. Okay, so 8 millimeters. I want to get rid of millimeters, and that 10 stays with the smaller. So this time it goes on the bottom. So I am just flipping the same conversion factor because I'm going in the opposite direction, and my answer here is 0.8. All right, this is a 1, this is a 10 to the minus 2. They are 100 apart from one another. So, more room. Okay, woohoo. Up, so let's see. Yeah, I've got just about enough room. So, 100 centimeters in a meter. So 5.6 meters. Want to get rid of meters. Put it on the bottom. 100 of those smaller ones. So my answer here is, I'll do a different color. 560. Okay. And then our last one, milli, 10 to the minus 3. This is a 1. So there are 1,000 of those smaller, so 120 milligrams. I want to get rid of milligrams. Put the 1,000 milligrams on the bottom because that's the smaller. They're 10 to the third apart. So 1,000. 1 gram on top, and my answer here is 0.12 grams. All right, that's the beginning of our unit conversions, and we'll stay with it for the rest of the semester since we are putting all of the math here in the second half of the course. And that concludes lecture number 1, and we'll get started on lecture number 2.